Hello, everyone. Welcome to week 11, or the beginning of week 11 with advanced exercise physiology. And we're talking this week for chapter 6, on chapter 6 with principles for testing and training for aerobic power. It's chapter 6 of 10, and 10 chapters are intended by the end of this semester. There is the possibility we won't get through all 10, so I don't want you to stress about that. We're not going to force the issue in that regard. It's the hope. The expectation is we'll be through with chapter 6 by the end of this week, maybe Monday of next week, being the 30th of March, and going into chapter 7, either the first part of next week, week 12, or middle of the week. I don't think chapter 7 is going to take us more than a little over a week, week and a half. So we'll probably get through at least 9 chapters, maybe 10. We'll see how it goes. That said, in addition to what is going to be 3 lectures this week on chapter 6 that should comprise the totality of the chapter. We'll see how that goes. I don't want to force the issue with too long of lectures for you, just like we wouldn't have if we had class live. We would not go more than that 50-minute time frame. Not going to do that to you. That being said, you do have an exam this week. It is going to cover chapters 4, 5, and 6, but you do not have to have that exam done until the end of Sunday. So lectures will all be in, but like as they would normally by Friday, we'll have all 3 lectures in. And of course, unlike live class, as much as it's difficult to look at video versus sitting in class, at least I think it is. I'd much rather be live and in class with a person to talk to and whatnot. Obviously, we can't have that right now. But the reality is, the good thing is, you can actually come back and look over videos again, fast forward, rewind, look at the content, and kind of move back and forth to kind of see content areas that you want to look over again and again. And that's the nice thing about having videos versus having live classes only. There's an advantage there. That being said, as always, email me with questions. I think what I may end up doing is actually having a specific discussion board posting for all questions. I need to get that up sometime soon. So as you have questions in the short term, email me with questions about content or anything for that matter. And then what I think we'll have done very soon, or we'll have up for you, is a discussion board for any questions you have over any area of the content at any time, and I'll just periodically check that every couple days. And if you need a response within less than 48 hours, I'm going to try for 24, but if you need it within less than 24, like within an hour, within 2 hours, you got to email me and let me know that route. Okay, I can't imagine you'll need that, but if you do, then you have that going for you as well. That said, let's talk about principles for testing and training for aerobic power. Talking first about the idea of aerobic power, which is synonymous with VO2 max. We're talking about the development and maintenance of aerobic power being vital for human performance and health-related physical fitness. Whether you're going for fitness or just overall health, it's important, which we've talked about before, and that shouldn't be terribly surprising. That said, the ability to transport and utilize oxygen isn't just vital for endurance sports, which a lot of people think that it is. It's more than just endurance sports. Anybody needs to be able to keep breathing under control, to be able to have energy for longer periods, right? And sport and fitness, but of course the ability to prolong daily fatigue, prolong it, to keep it from happening, or prevent daily fatigue, we should really say, from normal activity, let alone avoiding kidney failure or heart failure, and having a higher level aerobic capacity, ability to perform at higher levels of aerobic power, thus having a higher metabolic rate, all the above, is going to help with having less incidences of kidney or heart failure. Like all things, you can't stop everything, but you can certainly reduce probability of having major challenges like that. Now, that being said, a few important points that we need to make sure we have clear. You should probably have clear at this point already. Force is mass times acceleration. And when we're talking about mass times acceleration, your book doesn't talk about it, but I thought I'd throw it in there. Should also be talking about torque from the standpoint of, force is a matter of with the size of your object and the speed at which it's moving. Sure, that's true. How much force is required to speed something up, to slow it down, or hold it still, right? That being said, torque is a big component there too, relating to the angle involved, the amount of the distance from a given axis, from the axis point, how far away from like a limb, from basically where the load is relative to your shoulder, something like that, as well as from a standpoint of position in space, angle, and the amount of force as a whole on that point. So you got the amount of force, the angle, and the distance from the axis point. A lot involved there, more than we'll be talking about physiology, but we have to make sure we understand it's a little more complicated than is noted in the text. The text tried to refer to power, talking about a pull-up, which is the body weight, and then that is just moved. And like, well, you've got more going on than that. Limb length plays a great role with that. Hand position plays a role with that. It's not quite as simple as saying work performed. Like from a very general standpoint, yes, technically true, but not really going to tell you the whole story. Now, work equals force times distance. So if you obviously performing or performing work like walking a mile versus jogging a mile versus running a mile, we can talk about power as well. The amount of force you produce walking is certainly going to be less than the force you produce when you're jogging or running, much more force output, right? Generating higher, force output to get you off the ground. At some point when you run, you have both feet off the ground. Jogging, you can actually still have one foot on the ground. And walking, you absolutely have, in most situations, both feet on the ground a large majority of the time. That compared to certainly to jogging. That being said, when we talk about power, we're talking about work over time. So in other words, we're talking about the force times the distance over time. If we want to really be clear, be mass times acceleration times distance over time would be your power. And when people talk about power, they'll say so-and-so is very powerful. Well, anytime you do produce more force, move at a greater distance, or you basically essentially move it, accelerate at a higher rate, then you're looking at doing more work. That said, if you really want to improve power, you've got to do those things, go faster, produce more force, go over greater distances in less and less time, right? And as I mentioned, walking versus jogging versus running a mile, go over the same distance in more or less time is going to affect power. Time's your greatest factor involved with what affects power versus other aspects of producing force, okay? Now, the amount of oxygen consumed, the volume of oxygen, VO2, at rest or during any task or exercise is equivalent to the heat, kilocalories produced, right? We use kilocalories as our measurement of heat, and you can, by measuring oxygen consumption, you can determine calories used. That said, VO2 is an indirect measurement of heat or energy used, because the precise amount of energy used depends upon what nutrients being metabolized. So you need much more sophisticated equipment to be able to do that than just measuring oxygen, to be perfectly clear. That said, it's pretty difficult to be really perfectly accurate without some really expensive equipment. And we often utilize oxygen uptake as our primary determinant of energy usage using something called indirect spirometry, which is something we actually showed when we did the RER test when we were doing it in one of our labs a few weeks ago. It feels like years ago, just a few weeks ago, right? So much has happened between then and now. That said, the spirometer is an instrument for measuring, is used as an instrument for measuring lung capacities, right? And now a direct calorimeter, which is basically inside a large chamber, essentially, will assess changes in water temperature surrounding a vessel or an object. It's a very controlled atmosphere. It's very expensive, and there's other challenges too, which we'll talk about here in a moment here. But that said, when the body expends energy during work, heat's produced, right? And that transformation of chemical energy, ATP, or utilization of whichever energy substrate we're using, is transferred into or transformed, we should say, into mechanical energy or muscle energy for movement. And that whole process liberates heat. And each increase, and you probably heard this before, you recall this from bio or from anatomy and physiology, hopefully numerous times over. You probably can recite this by rote, I hope, that each increase in water temperature of 1 degree Celsius per 1 kilogram water is basically 1 kilocalorie of energy. So the calorie is simply a measure of how much heat's required to, or how much basically work is required to raise 1 degree water, 1 degree Celsius, 1 kilogram of water, 1 degree Celsius. Okay, so it's not the end-all be-all, but it's what we use for measuring oxygen, measuring our metabolic rate, our caloric usage. That said, stuff. Like I said, we talked about before. If I don't take it off my PowerPoints, like I didn't there, then it stays on there. It's supposed to be giving points for me for later usage. That said, for aerobic power and calorimetry, precise caloric determinations require use of something called a bomb calorimeter. A bomb calorimeter where food is ignited and burned, with the increase in circulating water being the equivalent energy of the food. Okay? That said, now that's precise. It takes a lot of time, requires expensive equipment, really expensive equipment, and it can still vary with the same foods. It's a really interesting point people don't talk about a lot. You take 2 potatoes of the same size, a same batch, basically from the same location, and you could get a different caloric breakdown of that same general potato looking like the same thing as before. Maybe one's a little bit older than the other one is. Maybe it's something different, slight variation in basically what it's been exposed to as far as being for the elements and whatnot. I mean, so many variables are there. You can't even be sure when you say you eat this food, it gives you 200 calories. You got to really be careful with that. We can really vary 10% or more, in some cases up to 30%. Pretty dramatic differences in the same natural foods, let alone the processed stuff we can sometimes eat, right? And that can also vary with the rapid changes in energy expenditure that occur with non-steady state exercise. It's really difficult to measure caloric usage when we're not in a steady state because there's so many variable metabolic responses that can't really properly be accounted for. So we have to take that into account as well. Now that said, the amount of oxygen consumed during activity can provide caloric usage. And of course, the energy associated with 1 liter of oxygen consumed is approximately 5 calories. Okay. Now that bomb calorimeter values and net energy values may differ, however, the net energy versus the bomb calorimeter values due to energy needed to digest nutrients. Carb takes 2%, fat takes 5%, protein 8%, and protein takes more due to the need to eliminate nitrogen in the urea from protein. And that, of course, yields a lower net value, which is ultimately what gives us our 4 kilocalories for carb, in protein, 7 kilocalories for alcohol, and 9 for fat. Okay. Now, oxygen uptake can be used to describe energy production, and it can be determined by measuring Q, cardiac output, which is heart rate times stroke volume, right? We need very expensive equipment to measure actual stroke volume. We can estimate it with a pulse pressure, but it's not fully accurate. Versus heart rate, we can actually determine, right? And of course, the arteriovenous oxygen difference, basically the oxygen in the arteries, basically flowing to the muscles that are basically into the system, and of course, the veins, what comes back, right? And what we breathe out, right? Of course, that requires sophisticated equipment, and it's highly trained personnel to manage to be properly accurate. So we often use, however, indirect open circuit spirometry, which can also be just as accurate, much easier to do, and it's close enough whereby it's reasonable to say it's just about as accurate as doing much more expensive testing. Okay, what they used to use back in the day, like decades ago, Douglas bags. You'd have a very obtrusive mask attached to your face, and you have a bag behind you. And basically you're carrying this bag on you. And they also use meteorological balloons, something you had to hold. Okay? There are old school manual methods to measure volume of air that can be very accurate if they're under proper controls, and measuring the oxygen and carbon dioxide concentrations in the air. Now, after making some adjustments to the measured volume of exhaled air, measured volume of what you exhale out, we can compute the volume of oxygen and carbon dioxide in the inhaled air. Okay. Now, similarly, if we measure the concentrations of oxygen and carbon dioxide in exhaled air, given our measure of the exhaled air, we can compute the volume for oxygen and carbon dioxide in the exhaled air. Okay. And that, of course, allows us to compute the volume of oxygen and consumed and the carbon dioxide produced. That's kind of the rough breakdown in spirometry, how we were figuring out those numbers. They come for our values of oxygen and carbon dioxide. Now, in aerobic testing, rather than requiring samples from a bag, like going old school, the Douglas bags and meteorological balloons, where we're filling our bag with mixed air sampled over time, we now have semi-automated electronic systems for breath-by-breath analysis. We've used that before with iWorks. We've seen that in class, and there's other machines that do the same thing. And these machines have advanced computing capabilities. They have portability, the ability to interface with software, semi-automated calibration, continuous monitoring or porting, sorted by your choice of time intervals, which is really advantageous to be able to use that way, and system capture of the ambient temperature in the room, essentially, or in the environment where you are, and barometric pressure, which, as we talked about before, or I think we've talked about for this class, or maybe you recall, the barometric pressure at sea level is basically 760 millimeters mercury. And of course, as you go higher in elevation above sea level, that can go down, 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 down. You'll still have the same breakdowns of about 79% nitrogen, just under 21% oxygen, and basically less than 0.5% of carbon dioxide, but you'll have less available the higher in elevation you go because the barometric pressure is dropping as you go up in altitude or elevation. Okay. Now, steady state. Steady state is a constant exercise pace whereby your heart rate and your VO2 are relatively unchanged for a moderate duration. Roughly, typically speaking, it's 10 to 30 minutes. Now, it takes a little bit to get up to steady state, and it's got to be something you can actually maintain for 10 to 30 minutes to really be referred to as a steady state. So it can't be too intense. For the person that we're training or talking about, they have to be able to maintain that pace, that same pace. That's why they call it steady state. If not, then, well, clearly it's too intense for the individual performing the work. That said, your gross VO2 during steady state submaximal exercise is about 2 liters a minute. Okay, 2 liters a minute of oxygen, whereas resting VO2 is about 0.3 or a liter or a third of a liter per minute. Okay, now once you reach that physiological state, which is within about 2 to 4 minutes, now typically depending on the fitness and the presence of illness or disease, it could be sooner or it could be later. It just depends on a lot of factors. That said, it's not surprising. We talked about how your aerobic energy system kicks in about 2 to 3 minutes in. That's why it varies in that 2 to 4 minute window. They found from a large majority of people, that 98% of people in that bell curve are going to fall within that 2 to 4 minute window, reaching steady state at a steady state of exertion, but they're not referred to as steady state aerobically until you hit that 2nd to 4th minute, somewhere in there. In which case, the VO2, the volume of oxygen, and the VCO2, the volume of carbon dioxide. And sorry, I got kind of lazy in this PowerPoint with not subscripting my 2s for showing some of these values. I did the same for showing some of the breakdown with glucose and with fat here shortly as well. So apologies there. That said, after you reach steady state, and after steady state has been reached, the values measured over a subsequent 1 minute interval can be used for calculations to determine utilization during steady state. Okay. Now, that said, before steady state can be reached, energy is produced in the absence of oxygen, anaerobic, right? That first couple minutes-ish. That's mostly glycolytic, typically because the first 10 to 30 seconds is about where somewhere in there you kick into more glycolytic energy production. The first, like we said, 1 to 2 seconds, maybe 1 to 5 seconds is ATP. Somewhere in that 2 to 10 seconds is typically creatine phosphate. And somewhere, typically speaking, arguably though, creatine phosphate could be the predominant energy system up to about 30 seconds. Unusual, but can be. And that said, depends on genetic differences, depends on training background, a lot of variables there, current conditioning. But somewhere in that 10 to 30 second time frame is when glycolysis kicks in as the primary energy system. So it's going to be mostly glycolytic, that 10 seconds-ish or 30 seconds-ish up to about that 2 to 4 minutes, give or take in there, arguably, for most people. Okay. Now, that said, energy is still needed to replenish ATP and creatine phosphate to clear lactate, not lactic acid, clear lactate, right? Following the cessation of exercise. So as you progress post-training into the recovery period, producing not OAT, but O2 debt for that recovery period. And that's often referred to as that exercise post-oxygen consumption. And people talk about like it's something you're trying to achieve. We'll talk more about that. That's not something we're going for, not something we're trying to get. It's not a positive thing. It is what it is. You exerted at a significant level, and now your body's trying to recover back down toward normal. And there's that period of time whereby from the exercise, the exertion related to duration and intensity, basically however long, based along with someone's conditioning and someone's general condition or state in that given moment, that day, they may have a shorter time toward coming back toward normal or a longer duration. Again, we'll talk more about that epoch in one of our later lectures during this week. Recovery period is going to always be, interestingly enough, is kind of an interesting point to note, always equal to the energy required to replenish energy stores and clear lactate from the blood. So in other words, you'll need a longer recovery if you worked out pretty intensely and you're kind of out of shape. You're going to have a longer state of epoch. It's not a good thing. It's a recognition of your lack of conditioning or lack of capacity to recover quickly from the exertion. Don't want to confuse that. Okay. Now, we can compute the kilocalories used in a given exercise, steady state wise, certainly easier to do, hard to do again if it's not steady state, by knowing the oxygen consumed. And that's about 5 kilocalories per liter of oxygen, right? And again, it's about 0.3 liters of oxygen used at rest per minute and about 2 liters a minute at submaximal steady state. Now, typically a VO2 max takes into account not just VO2 in liters per minute, but also liters per kilogram per minute, meaning your body weight, which makes sense, right? Can't just talk about utilization rate, you have to talk about relative to your size. Because obviously if two people are doing the same pace, performing the same work, and one person is 30 pounds heavier than the other person, their VO2 is off the charts relative to the person that's lighter doing the same amount of work. Okay? And that's basically peak aerobic power, and of course VO2 max are the same thing. Now, while 5 kilocalories is an average estimate of liters of oxygen consumed, the RER, or respiratory equivalency ratio, is a relationship between carbon dioxide exhaled per unit of time and the volume of oxygen consumed during the same interval, which will indicate what substrate we use, right? An RER of 0.7 or below is going to be 100% fat utilization, whereas somewhere in the 0.84 to 0.85 RER is about 50-50 fat to carb. Okay, and by the way, we talked about before, about 0.78 to 0.81 is somewhere around typical person sitting during their day doing very light work. The moment stress goes up a little bit, you're already in that 50-50 fat carb area right off the bat. Okay. That's why some people say typical light daily activities, sitting in a chair, is probably about 55 to 60% fat and probably about 45 to 50% or 40-45% carbohydrate. Still, carbohydrates right there, all depending upon how intense life is, right? As you get up to 1.0 RER, then we're looking at 100% carb utilization. Now, according to Avogadro's law, equal volumes of gases at the same temperature contain the same number of molecules. Now, what that means for us, and simply with carbohydrate, we have 1 mole of C6H12O6 or glucose plus 6 moles of oxygen becomes 6 moles of CO2, right? On the basically after expiration, plus 6 moles of H2O, and that basically comes out to be 6 VCO2, 6 in terms of the volume of carbon dioxide, and 6 for the volume of oxygen, which equals 1 RER, which is where we get carb utilization. Okay, that's where that comes from. That's the breakdown of how we get to 1.0 for 100% carb utilization. Now for fat, on 1 mole of C16H32O2 or like palmitic acid, basically plus 23 mole of oxygen, because it takes a lot more oxygen for oxidation of fat, right? A lot more oxygen here, comes out to be, we should say not equals, if it comes out to be or transforms to 16 moles of oxygen plus 16 moles of hydrogen to oxygen, water. And that comes out to be 16 for volume of carbon dioxide over 23 volume of oxygen, which is how they get the 0.7 RER for 100% utilization of fat. And that's where that comes from. That said, protein ingestion, if you eat protein, is going to dramatically affect that metabolic rate. Matter of fact, it's going to go much higher RER. If you don't have much carbon utilization there, your body's going to have a harder time. It's going to be from a standpoint of what would normally be a lower RER at the same steady state output. You're going to have a higher RER if you're ingesting a bunch of protein or not having any carb present in your system for your circulating glucose, or let alone stored glycogen to be using for exertion. Muscular, first from the muscle glycogen, then the liver glycogen, right? If it's not in circulation. That said, if you hyperventilate, also can dramatically throw off RER, which is not surprising. If you're exhaling at a very rapid rate, it's going to throw off the balance of recognizing what the test would normally be trying to measure in terms of oxygen and carbon dioxide. It's hard for it to measure accurately. Hopefully it doesn't happen in the first place, let alone something you want to try to do. And again, steady versus non-steady state exertion. Non-steady state is very difficult to measure accurately due to numerous variables metabolically. Steady states will really need, and of course, exercise type. If it's short and exhaustive versus being long and slow, can all affect RER. Okay. That said, there's my stuff again. I crack up with just how I seem to forget to take that off sometimes. Final thoughts. Your discussion board post for week 11 is up. It's due by Thursday, the end of Thursday, for the first post. And that's important you get that in. And then, of course, I'm going to get on there and try to respond to you, unlike last week, because I had you posting all of it to the very, very end. So a lot of you posted, most of you posted really, really late. I get that. Difficult first week, not even a full first week, going to online, right? That said, we really want to make sure that you get it posted in a reasonable time so people can respond to you, and I can respond to you, with all responses done by end of Sunday. So we're kind of working on a weekly basis now. We're not working on a day-to-day basis, working on a weekly basis. I'll try to keep you posted, keep you up to date. Email me if you ever have concerns. You got to do that. We'll have 2 more lecture videos this week, following this one between now and Friday. I'll supply study questions for you because you have an exam sometime by tomorrow. At some point there by the end of the day, before midnight or somewhere in that time frame. Maybe by the time you wake up on Thursday morning, you'll find it there. And it's also going to be your lab for the week. So you'll be able to complete your lab and prepare for the exam once again, as we did for the first exam. I thought that was a good process to be following. I can't say it'll be necessarily the same for the third exam, but I wouldn't be surprised if it is. I think it's a good way to go to make sure you're getting the material as well as help you prepare for the exam. And that said, it's going to be probably another 50-60 question multiple choice exam. It will be multiple choice, won't be anything else but multiple choice. But that said, it will not be more than 50-60 questions. It might be less. And I will tell you in advance, it is not going to be even as much as a minute per exam. This is an online exam. And the last thing I want to have you doing is trying to search through and find everything as the question pops up. You're going to have probably about 30 seconds a question. I know it sounds hardcore. That's why you got to prepare properly. So you can go ding, 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 and go right through that exam, not be trying to look stuff up. It's designed so you will not have that time to do that for the full totality of the exam. That said, that'll be due by the end of Sunday. And of course, your study questions are your lab report, as mentioned. Email me if you have questions at any time. Please let me know how you're doing. I want to make sure you're taking good care of yourself. And make sure you're doing the best you can with everything you have going on. Let me know any challenges you have so I can help any way that I can. All right. Take care until next time, guys.